Instrument transformers supply protective relays with current and voltage for measurement. This high current and voltage is first converted by the transformers to much lower quantities that can safely be injected into the relay for measurement. It is important to note that the proper selection of current and voltage transformers for protective relaying applications is the responsibility of the system engineer. CT's introduction. The function of a current transformer, or CT, is to take a current flowing through a wire or cable and step it down to a magnitude that a protective relay can measure. A primary characteristic of CTs is their conversion ratio. In this example, our conversion ratio is 100 to 5, meaning that if 100 amps are passed through the primary phase wire, the CT will scale this down to 5 amps and direct it to the relay via the secondary windings. The 5 amp measure is known as the secondary nominal current. If a fault were to occur on this phase that increases the primary current to 200 amps, then 10 amps would be passed to the relay through the secondary windings, consistent with the ratio. Types of CTs. A common current transformer construction is one in which the power system phase wire is passed through the hole in the center of an annular core or ring, which is called a window. This forms the primary winding. A second insulated wire is then wound around the core and then brought to the relay for measurement. This is known as the secondary winding. A CT with this type of construction is typically referred to as a toroidal or donut style of CT. A bushing type CT refers to a CT that is built into another power system device, such as a breaker. Terminals are provided on these devices to permit connecting the CT to a relay. A bar-type CT has a solid bar that passes through the annular core to form the primary winding of the CT. The primary phase wires of the power system are then connected directly to these bars to complete the connections. Potential transformers. The next type of transformer we will cover is the potential transformer symbolized as PT, or sometimes known as voltage transformers symbolized as VT. Similar to current transformers, potential transformers scale down the voltage passed through them, as opposed to the previously mentioned current. The scaled-down voltage is then routed to a protective relay for measurement. Also as in current, a PT is classified with a conversion ratio indicating the amount the primary voltage is scaled down. For example, 60 to 1 scales the primary voltage down to 120 volts. There are two different types of potential transformers used today: the electromagnetic voltage transformer and the capacitive voltage transformer. Electromagnetic voltage transformers are usually used when accurate metering needs to be performed for lower voltage applications. Capacitive voltage transformers are commonly used in high voltage transmission line applications where the voltage is higher than 66 kilovolts. Electromagnetic voltage transformers have dense winding drops designed to accurately scale down the voltage and make sure the ratio is consistent for all variations in the input voltage. Due to the small amount of voltage drops per winding, the electromagnetic voltage transformers will increase in size as the rated primary voltage also increases. Likewise, the cost of electromagnetic voltage transformers tends to increase at a disproportionate rate to the primary voltage rating. Capacitive voltage transformers, or CVTs, are normally used on higher voltage applications. The CVT is basically a capacitance potential divider and consists of the following components: coupling capacitors, typically 10, compensating reactor, step-down transformer, and a ferro-resonance suppression circuit that is found just before the output terminals for connecting to a relay.